Over 4.3 billion kilometers from the Sun, far beyond Neptune's faint blue rings, orbits a moon unlike any other in our solar system. Its name is Triton, and it defies expectations from the moment it comes into view. Orbiting its planet in the opposite direction of Neptune's rotation, it is a cosmic outlier, a frozen enigma suspended in the outer dark. Discovered in 1846 by British astronomer William Lassell, Triton has fascinated scientists and dreamers alike for nearly 2 centuries. Its surface is a frozen tapestry of icy plains, nitrogen geysers, and scars etched by unknown forces. With temperatures plummeting to -235 degrees Celsius, it may seem like the most unlikely place to find life. And yet, deep beneath its frozen crust, some believe there lies a subsurface ocean. Could this ocean shelter life? Could humans one day walk its surface or even live beneath its ice? Triton holds secrets, ancient, quiet, and profound, that stretch the limits of our understanding and imagination. In this audio journey, you will drift through 12 chapters of cosmic contemplation. We'll explore Triton's possible origin as a captured Kuiper belt object, its mysterious geology, and the tantalizing hints of activity beneath its icy shell. We will also ask what it would take, physically, biologically, and philosophically, to one day call this distant moon home. Each step in our journey will be slow and thoughtful, like floating through the shadow of Neptune, watching Triton glow faintly in the cold. This is more than just an exploration of a moon. It is an invitation to ponder one of the greatest questions we can ask. Where can life exist, and could it thrive where we least expect it?
Chapter 1. The Captured Moon, Triton's Unusual Origins. Long before human eyes ever glimpsed it, Triton had already lived through a cosmic upheaval, a journey across the solar system that left it unlike any other major moon. It is not merely a satellite orbiting a distant planet. Triton is a mystery of motion, a renegade body caught in the gravity of a giant. And understanding its strange beginning is the first step toward uncovering whether it could ever host life. Triton wasn't born around Neptune, at least that's what most planetary scientists believe. Unlike other large moons, which typically form in the swirling disk of gas and dust surrounding a young planet, Triton appears to have come from elsewhere, likely from the Kuiper belt, a region beyond Neptune filled with icy bodies and ancient remnants from the early solar system. These distant objects, called trans-Neptunian objects, move in elongated orbits and hold some of the oldest material in the solar system. Many believe Triton was once one of them. Some 4 billion years ago, this icy wanderer may have strayed too close to Neptune. In a moment both violent and graceful, Neptune's immense gravity seized it. The moon was captured, pulled into a retrograde orbit that now moves in the opposite direction of Neptune's rotation. This detail alone sets Triton apart. No other large moon in the solar system orbits its planet backward. This unusual orbit is one of the strongest clues that Triton is a captured world. But the story gets even stranger. The act of capture wasn't smooth. It would have been a chaotic event, possibly involving a collision or gravitational interaction with another body. Some theories suggest Triton was once part of a binary system, 2 Kuiper belt objects traveling together. Neptune may have captured one while the other was flung away into the void. The resulting tug-of-war caused Triton to spiral inward slowly, settling into its current orbit. In doing so, it likely disrupted or even destroyed Neptune's original moons, which couldn't survive the gravitational chaos. All of this makes Triton something rare, a foreign moon, imported from the outer reaches of the solar system. It is not merely a satellite, but a visitor, perhaps even a kind of fossil, from a time when the planets were still forming and the solar system was wild and unpredictable. This origin has profound implications for the possibility of life. If Triton formed far from Neptune in the icy Kuiper belt, it may carry different materials than moons that were born around the planet. These materials, volatile ices, complex organics, and exotic compounds, are essential pieces in the puzzle of habitability. And the very act of being captured might have generated enough internal friction or tidal heating to warm the moon's interior. That warmth may have been fleeting, or it may still linger. And if it does, if some of that ancient heat remains trapped beneath Triton's icy shell, it could be sustaining something extraordinary, a hidden ocean locked beneath the surface, shielded from the cold vacuum of space. It is in this context that scientists begin to wonder, what if Triton isn't just interesting, but potentially alive? Of course, no spacecraft has landed there. Only one, NASA's Voyager 2, flew by Triton in 1989, capturing haunting images of its pale terrain and streaked surface. The data revealed unexpected geological activity, including geysers of nitrogen erupting from its crust, a sign that Triton, despite its deep freeze, is not geologically dead. That brief encounter showed us only a glimpse, a moon with a strange past, a backward orbit, and an origin story unlike any other, a moon that shouldn't be there, and yet is. In the quiet reaches of the solar system, far beyond where sunlight warms the ground, Triton drifts, a captured traveler carrying ancient secrets and new questions. As we begin this slow journey through its mysteries, we must remember, Triton did not choose Neptune. It was pulled in, reshaped, and now held in place by forces it cannot escape. And yet, in its capture, it may have become one of the most fascinating places in the cosmos, a cold moon with the potential to host life where none should exist.
Chapter 2. Dancing Backwards. Triton's Retrograde Mystery. Triton orbits Neptune in reverse. This simple fact, on its own, breaks the usual rules of planetary motion. Most major moons in the solar system travel around their planets in the same direction the planets spin, what we call prograde motion. It's a natural consequence of how moons typically form, coalescing from the same spinning disk of gas and dust as their host planets. But Triton does not follow that script. Instead, it moves backwards, tracing a retrograde orbit, defying the rhythm of Neptune's rotation. This strange orbital dance is more than a quirk. It's a cosmic red flag, a clear indication that Triton did not form around Neptune. It was captured. But that capture, while possible, came at a price. Retrograde orbits are rare, especially for moons as large as Triton. In fact, Triton is the only major moon in the solar system that moves this way, orbiting against the flow. Its path is tilted too, inclined by more than 150 degrees relative to Neptune's equator. It's as if the moon arrived from elsewhere, out of sync with the system, and was forcibly inserted into an environment that never expected it. This insertion wasn't clean or gentle. Theories suggest that when Triton was captured, perhaps from the Kuiper belt, it entered into a wild elliptical orbit, careening around Neptune with great energy. Over time, this orbit was smoothed and circularized by a process called tidal evolution. In this process, Neptune's gravity tugged at Triton again and again, reshaping its path while generating internal heat through friction. That heat may still echo deep within Triton's interior, a fact that becomes increasingly relevant as we explore its potential for life. But Triton's retrograde orbit has another implication. It is unstable in the long term. While it may seem serene now, slowly circling its host at a distance of about 355,000 kilometers, Triton is actually in a kind of slow-motion fall. Each orbit brings it ever so slightly closer to Neptune, dragged inward by the same tidal forces that once warmed its interior. Someday, though not for billions of years, Triton may spiral so close that Neptune's gravity will rip it apart. Its fragments could then form a majestic ring system, temporarily turning Neptune into a new Saturn. This poetic fate underscores the tension in Triton's existence. It is both prisoner and performer, held in a delicate balance that cannot last forever. But for now, Triton remains in motion, smooth, quiet, and persistent. Its retrograde path also creates subtle effects on its environment. Tidal interactions between Moon and planet are amplified, producing stresses in Triton's crust. These forces may contribute to the Moon's surprising geological activity, including the nitrogen geysers first observed by Voyager 2. In some ways, the backward motion may be keeping Triton alive, stretching and warming its icy shell in ways no other moon experiences. For scientists, Triton's retrograde orbit provides both a puzzle and a promise. It is evidence of a violent past, a disruptive event that shaped not only Triton, but Neptune's entire moon system. It's likely that Tritons captured, disrupted, or even destroyed pre-existing moons, leaving behind the sparse and irregular satellite system Neptune has today. But that disruption also made Triton unique. Its retrograde dance is a kind of celestial signature, a whisper of where it came from and how different it really is. While other moons settled quietly into the orbits they were born with, Triton carved its own path, resisting the spin of its parent, telling a story that runs counter to the expected. And it's this difference that makes Triton so intriguing in the search for life. Because if a world can survive such upheaval, can move backwards through space and still remain geologically active, still potentially hide an ocean beneath its surface, then perhaps it can also surprise us in other ways. Perhaps it holds life too, or at the very least, the conditions that could one day allow it. Triton moves in defiance of expectation. It dances to a rhythm all its own, and in doing so, it reminds us that in the vast silence of space, the most interesting stories are often the ones that spin in reverse.
Chapter 3: A Frozen World in Motion, Geysers and Surface Activity. At first glance, Triton appears lifeless, a pale, icy moon suspended in the distant reaches of the solar system. Its surface is smooth and bright, coated in frozen nitrogen, carbon monoxide, and methane. There are few visible craters, which is unusual for such an old celestial body. But the reason for this becomes clear with a closer look. Triton is not frozen in time. It is moving, breathing, and changing, even in the coldest of places. In 1989, NASA's Voyager 2 became the first, and so far the only, spacecraft to visit Triton. As it passed by the moon, its instruments detected something completely unexpected. Plumes of nitrogen gas erupting from the surface, some stretching more than 8 kilometers into the thin atmosphere. These geysers, invisible until sunlight caught them just right, revealed that Triton was geologically active. This discovery stunned scientists. Before this, the outer solar system was thought to be largely quiet and inert, especially on moons so distant from the sun. But Triton shattered that assumption. It became clear that beneath its frozen crust, something dynamic was happening. These geysers are thought to result from cryovolcanism, a process similar to volcanic activity on Earth, but instead of molten rock, it involves the eruption of icy substances like water, ammonia, and methane. On Triton, The sun's faint warmth may penetrate translucent layers of frozen nitrogen, causing trapped gas to build up pressure until it violently escapes through surface vents. The gas bursts forth, dragging dark particles with it and staining the ice in long, wind-blown streaks. Voyager's images showed that these dark streaks cover vast areas of the southern hemisphere, creating patterns of activity that may shift with Triton seasons. It's a moon that, despite its frozen exterior, shows signs of weather, of internal heat, and of geological renewal. These features make Triton one of the most Earth-like and yet alien landscapes beyond our planet. The geysers also suggest that Triton has a layered internal structure, with some form of energy still active beneath the surface. Whether this energy comes from the decay of radioactive elements, the residual heat from its violent capture by Neptune, or the tidal stresses of its eccentric orbit is still unknown. But the result is clear. Triton is not geologically dead. This matters deeply when we talk about the potential for life. A frozen surface, left untouched for billions of years, offers little hope for biology. But an active world, one with changing terrain, flowing materials, and internal energy is far more promising. Life, at least as we know it, depends on chemistry and motion. It requires not just ingredients, but the stirring, shifting environments where those ingredients can combine. Triton's cryovolcanism may help circulate materials from deep within the moon up to the surface, and perhaps even vice versa. This could create exchange zones where different environments interact, places that, on Earth, are often teeming with life. It also raises the possibility of a subsurface ocean. If Triton's interior is warm enough to fuel geysers and support cryovolcanism, then it may also be warm enough to melt some of its icy core, creating a liquid ocean beneath the crust. Such an ocean would be sealed beneath kilometers of ice, shielded from radiation and cosmic debris, but warmed from below. A quiet, dark sea in the farthest reaches of the solar system. This idea is not science fiction. Other moons, like Jupiter's Europa and Saturn's Enceladus, are now strong candidates for life, precisely because of similar internal activity and subsurface oceans. Triton may belong in that same rare category. And yet Triton remains mostly untouched. Voyager 2's brief flyby lasted only a few hours, capturing less than half of the moon's surface in detail. There is still so much we do not know. Could these geysers still be active today? Could they be even more widespread than we imagined? Could they be venting material from an alien ocean? No one can say for sure, not yet. What we do know is that beneath the ice, Triton stirs, it shifts, it exhales, and it tells us that in the deep, dark cold of the outer solar system, motion is still possible. And where there is motion, there may be life.
Chapter 4. Beneath the Ice. Clues of a Subsurface Ocean. Triton's surface is a frozen wasteland, dazzling white and ghostly pale, with the temperature hovering near absolute zero. But beneath this layer of nitrogen ice lies one of the most tantalizing mysteries in planetary science. Could there be an ocean hidden beneath the crust? It may seem impossible. After all, Triton is one of the coldest objects in the solar system. With surface temperatures plunging to minus 235 degrees Celsius, minus 391 degrees Fahrenheit, it is colder than Pluto, colder than any place known to harbor the conditions for life. And yet, in the stillness below its icy shell, there may be warmth. Not the kind of warmth that melts glaciers into rivers, but something deeper, ancient heat locked away from the stars. One of the most compelling pieces of evidence comes from Triton's own geological activity. As we explored earlier, Voyager 2 observed geysers venting nitrogen gas from beneath the surface. These plumes suggest that energy is moving from Triton's interior to its exterior. And for that to happen, there must be heat. But where does it come from?
There are a few possibilities. One is radioactive decay, the natural breakdown of unstable elements in Triton's rocky core. Even a small amount of these materials can generate enough heat over billions of years to maintain a layer of liquid beneath the ice. Another possibility is tidal heating. Though Triton's orbit is now nearly circular, it wasn't always that way. In the distant past, its eccentric orbit around Neptune could have caused immense internal friction, warming the moon from within. But heat alone isn't enough. For an ocean to exist, Triton must also contain materials that lower the freezing point of water. Compounds like ammonia or methanol, which act as natural antifreeze. And scientists believe such ingredients may be present. They've been found on other icy bodies, and Triton, with its likely Kuiper belt origin, may be especially rich in exotic ices and volatiles. So, what would this ocean be like? It would be nothing like Earth's sunlit seas. It would be a dark, pressurized realm sealed beneath tens of kilometers of frozen crust. The water would be briny, laced with ammonia and other compounds. There would be no surface light, no sky, no weather, only the silent shifting of water warmed by rock below and shielded by ice above. Yet, this kind of environment, as alien as it may seem, is not without precedent. On Earth, life has been found in the most extreme and isolated places, in deep ocean trenches, inside Antarctic lakes buried beneath miles of ice, and near hydrothermal vents where sunlight never reaches. In these places, life doesn't rely on photosynthesis, but on chemosynthesis, a process that uses energy from chemical reactions, often involving sulfur or methane, to fuel biological activity. If Triton does contain a subsurface ocean, it is possible, just barely, that it may harbor similar forms of life. Tiny, simple organisms clinging to rocky vents, drawing energy from the same heat and minerals that warm the ocean itself and shielded by ice above. We would never know they're there by looking at the surface. They would be hidden, invisible, enduring in silence beneath a world locked in ice. Scientists are increasingly convinced that oceans like this may be common in the outer solar system. Europa, Enceladus, Ganymede, and perhaps even Pluto may all possess subsurface seas. If Triton is part of this group, it opens the door to a staggering realization. Life in our solar system might not be confined to the habitable zone around the sun. It might exist in the cold, dark outskirts beneath the ice. Of course, we haven't yet confirmed the ocean on Triton. The data we have is limited, and no new mission has visited the moon since Voyager 2. But new future spacecraft, such as NASA's proposed Triton mission, may change that. With advanced instruments, seismometers, radar, and thermal detectors, we could finally peel back the crust and listen for echoes beneath the ice. Until then, we can only imagine what lies beneath. A still sea, untouched for billions of years. A silent ocean, moving slowly in the dark. A possible cradle for life, not as we know it, but as it might emerge in the cold, enduring places of the cosmos. And in that vast silence, Triton waits, guarding the secret of its hidden ocean, and perhaps the distant echo of something alive.
Chapter 5. The Chemistry of Possibility. Ingredients for life on Triton. To search for life is to search for chemistry. Beneath every cell, every heartbeat, every breath, there is a dance of molecules, carbon bonding with hydrogen, oxygen linking with nitrogen, and energy pulsing through chains of reactions. Life,
at its most fundamental level, is a chemical phenomenon. And if Triton is to be considered a candidate for life, we must ask, does it have the right ingredients? On Earth, life depends on a small handful of key elements, often summarized by the acronym CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements form the backbone of DNA, proteins, cell membranes, and energy molecules like ATP. But equally important are the conditions in which these elements can interact: water, energy sources, and time. Let us begin with water. Though Triton's surface is composed mainly of frozen nitrogen and methane, scientists believe there may be liquid water below, mixed with ammonia and other antifreeze compounds. This underground sea, if it exists, could serve as a stable environment for chemical interactions, a kind of cosmic test tube sealed beneath kilometers of ice. Water is not just a solvent, it is a medium of transformation, allowing atoms to meet, react, and evolve into more complex molecules. Then comes carbon, the versatile element at the heart of organic chemistry. Carbon is common in the outer solar system, found in the form of methane, CH4, or carbon monoxide, CO, and complex organics coating icy bodies. On Triton, methane is abundant on the surface and likely deeper below. Over time, with the influence of radiation and chemical energy, simple carbon molecules can form tholin-like compounds, reddish, tar-like materials that hint at prebiotic complexity. Nitrogen, too, is plentiful on Triton. Its frozen form dominates the moon's outer layers and fuels its mysterious geysers. On Earth, nitrogen is essential for building amino acids and nucleic acids, the building blocks of proteins and genetic material. If similar chemical reactions occur within Triton's ocean, nitrogen could play a key role in any emerging biochemistry. Hydrogen is widespread in ice and organic molecules and often pairs with oxygen to form water. But perhaps most intriguing is the role of energy, the spark that allows molecules to combine, break apart, and rearrange. On Earth, this energy often comes from sunlight, but in the darkness of Triton, other sources must be at work. One candidate is tidal heating. Though less intense than what we see on moons like Europa or Enceladus, Triton's history of orbital evolution may have generated enough internal warmth to power chemical reactions. Another possibility is radiolysis, in which radiation from cosmic rays or Neptune's magnetosphere splits water molecules into reactive fragments, free radicals that can initiate complex chemistry. Even the geysers observed by Voyager 2 may suggest surface-interior exchange, material from deeper layers being transported upward, possibly mixed and processed by thermal and chemical forces before freezing into the crust. If Triton's ocean communicates with its surface in any way, even through microscopic cracks or slow diffusion, it could serve as a bridge, allowing chemistry to circulate, evolve, and build complexity. But what about phosphorus and sulfur? These two elements are less well understood in Triton's context. Phosphorus is rare in the universe, but essential for life as we know it. It's the backbone of DNA and a critical component in energy transfer molecules. If Triton's rocky core contains phosphorus, and if that core interacts with the ocean below, it could be enough. Sulfur, meanwhile, is more common in icy moons, especially those with volcanic or hydrothermal activity. It's unclear whether Triton has the same geochemistry, but its captured origin from the Kuiper belt may have endowed it with unique sulfur-rich compounds. Ultimately, the chemistry of Triton remains a silent promise, a set of potential ingredients locked in cold stone and ice, waiting for us to ask the right questions. We don't know if those ingredients ever mixed in the right way. We don't know if the conditions lasted long enough. But the possibility exists, and that possibility grows stronger when we remember how little we truly need to make life. A few atoms, a bit of energy, and time. Billions of years have passed since Triton was captured. During that time, chemical reactions may have slowly taken place deep beneath the crust, hidden from every eye. They may have built nothing, or they may have built the first fragile scaffolding of life. No one can say yet, but the ingredients are there, or so we believe. In methane and nitrogen, in buried oceans and unknown minerals, Triton may hold the seeds of something more. And if those seeds exist, even in silence, then perhaps life, strange, slow, and alien, is already at home in the cold.
Chapter 6: Echoes of Europa and Enceladus, Comparing Ocean Worlds. In the great darkness beyond Mars, scattered across the outer solar system, lie a family of hidden seas. They are not warm, sunlit oceans like those of Earth. They are buried, secret, silent, cradled beneath crusts of ice and time. Among these icy ocean worlds, a few have become favorites in the search for life. Europa, the fractured moon of Jupiter, and Enceladus, the brilliant pearl of Saturn. But now, scientists are beginning to wonder, could Triton belong in this same group? To compare these worlds is not to diminish their uniqueness, but to draw patterns from possibility. Europa, slightly smaller than Earth's moon, has long been one of the most compelling candidates for alien life. Beneath its cracked surface of water ice, evidence suggests the presence of a global ocean, one that may be twice the volume of all Earth's oceans combined. The surface is etched with ridges and bands, signs of shifting ice plates and subsurface currents. Its tidal heating, caused by gravitational tugging from Jupiter and neighboring moons, may keep the ocean liquid. And beneath that sea, hydrothermal vents could provide the chemical energy needed for life. Enceladus, meanwhile, surprised the world in 2005 when NASA's Cassini spacecraft flew through its southern plumes, jets of water vapor, ice, and organic molecules spraying into space. These geysers, erupting from fractures called tiger stripes, revealed a salty ocean beneath a relatively thin shell. Enceladus may be small, but its active interior and accessible chemistry have vaulted it into the spotlight of astrobiology. Both of these moons share certain qualities that make them especially interesting: a subsurface liquid ocean, internal heat, organic chemistry, and signs of ongoing activity. These are not just icy rocks, they are dynamic, evolving systems, quietly stirring in the dark. Triton, though more distant, begins to echo these qualities. Like Europa and Enceladus, Triton shows signs of a subsurface ocean. Its retrograde orbit and strange geology suggest a dramatic past that could have provided enough energy to melt its inner layers. And while no spacecraft has flown through its plumes yet, Voyager 2's detection of active nitrogen geysers proves that Triton is not dormant. Something beneath the surface still moves. But there are key differences too. Triton is larger than both Europa and Enceladus. Its origin is likely different, captured rather than co-formed, and its surface composition is more varied, with frozen nitrogen and methane dominating its landscape. While Europa and Enceladus orbit gas giants close enough to feel strong tidal forces, Triton's heating may be subtler, drawn more from ancient orbital interactions and the slow decay of radioactive materials. This could make Triton's internal ocean colder, more sluggish, but possibly still stable. There's also the question of surface access exchange.
On Enceladus, the plumes shoot directly from the ocean into space, making it easy for spacecraft to sample it without landing. Europa's ocean is more isolated, but scientists believe fractures in the ice may occasionally allow material to rise and fall. Triton's geysers, on the other hand, are likely powered by surface heating and pressure buildup, not necessarily connected directly to an inner ocean. Still, the surface may hold traces of deeper chemistry. If even a small pathway exists between the ocean and the surface, a crack, a tunnel, a fault, it could allow organic molecules to rise, freeze, and preserve themselves for eons. Another similarity between these worlds is their quiet rebellion. They defy expectations. Where we once assumed the outer solar system was too cold, too dead, too far, these moons whisper otherwise. They remind us that life does not need sunlight or warm skies or even continents. It only needs a little warmth, a little water, and enough time. In that sense, Triton is part of something larger, a new class of worlds, ocean worlds, alien aquifers, dark seas. Together, they suggest that habitable environments might be far more common than we imagined, not only on planets like Earth orbiting in the narrow band of the habitable zone, but deep in the cold shadows of distant giants. Triton may be more isolated, more difficult to reach, more enigmatic, but it belongs to this family of possibilities. A world of quiet ecos, frozen breath, and buried potential. A world waiting not just to be explored, but understood. If Europa and Enceladus are the songs we've already begun to hear, Triton is the distant hum, fainter, slower, but no less beautiful. And perhaps, when we listen closely enough, we'll find that all these worlds are singing the same tune, the melody of life hidden beneath the ice.
Chapter 7. Silence and Pressure. Could anything survive below? Beneath the thick ice of Triton lies a world of silence, a realm isolated from sunlight, storms, and seasons. It is a place where darkness reigns, where the crushing pressure of kilometers of ice presses down on a hidden ocean, and where life, if it exists, must find a way to endure in conditions that challenge everything we understand about biology. The ocean beneath Triton's surface, if real, is not a gentle sea. It is an environment of extremes, immense pressure from the overlying ice, near freezing temperatures, and complete absence of light. There are no green plants here, no photosynthesis, no warmth from a distant star. Instead, life would have to rely on other sources of energy, chemical reactions fueled by minerals and elements leaching from the rocky core below. On Earth, we find surprising analogs in places like deep-sea hydrothermal vents and subglacial lakes. These habitats, cut off from sunlight for millions of years, support ecosystems thriving on chemosynthesis, where bacteria convert chemicals such as hydrogen sulfide or methane into energy. Could similar processes power life beneath Triton's frozen shell? Pressure is another significant factor. At depths of tens of kilometers beneath the ice, pressures could reach hundreds of megapascals, many times greater than at Earth's deepest ocean trenches. While extreme, many microorganisms on Earth are known to survive and even thrive under high-pressure conditions, called piezophiles or barophiles. These resilient life forms adapt their cellular structures and metabolism to endure crushing forces, providing a model for what might exist in extraterrestrial oceans. Temperature is equally challenging. Triton's ocean, if present, is expected to be near the freezing point of water, possibly lowered by antifreeze compounds like ammonia. Cold temperatures slow chemical reactions and biological processes, but do not necessarily prevent life. On Earth, psychrophilic organisms thrive in polar regions, beneath glaciers, and in icy waters, proving that life is remarkably adaptable. The silence itself, the profound stillness of such an environment, raises questions about communication and sensory perception for potential life forms. Without light or sound in the conventional sense, organisms would need to rely on chemical gradients, electrical signals, or mechanical vibrations to navigate and survive. Moreover, the ocean's isolation implies that any ecosystem would be closed with limited inputs of new materials. Life would depend on recycling nutrients efficiently, perhaps evolving complex biochemical pathways to sustain itself over vast timescales. While speculative, these ideas are grounded in Earth's own extreme environments. The discovery of microbial life in places once thought uninhabitable has expanded our understanding of biology's limits. It encourages us to consider that life, if it ever arose in Triton's ocean, might be hardy, slow-growing, and vastly different from anything we know. Still, without direct exploration, these remain hypotheses. We lack evidence of life or even organic molecules beneath Triton's ice. But the potential is there, a silent world waiting to be understood, where pressure and cold create a realm of possibility as vast and mysterious as the cosmos itself.
Chapter 8. Terraforming Triton, Fiction or Future? The idea of making Triton habitable is a bold one. It pushes us beyond questions of natural possibility into the realm of human ambition and imagination. Terraforming, the act of deliberately altering a celestial body's environment to make it suitable for life, has long been a staple of science fiction. But with growing knowledge of planets and moons, it has become a topic of serious scientific and philosophical debate. Triton, with its frozen surface, thin atmosphere, and distant orbit, seems like one of the most challenging candidates for such an endeavor. Its average surface temperature hovers near -235 degrees Celsius, -391 degrees Fahrenheit, and its atmosphere is so thin that nitrogen geysers erupt like faint breaths from deep below the ice. The Moon orbits Neptune at a great distance, bathed in weak sunlight, barely enough to cast shadows. All of these factors combine to create an environment hostile to Earth life as we know it. But what would it take to transform Triton into a place where humans could survive or even thrive? First, the surface temperature would have to rise dramatically. This could involve introducing greenhouse gases into the atmosphere to trap more heat, a process that has been proposed for Mars. However, Triton's distance from the Sun means sunlight is about 900 times weaker than on Earth, so natural warming would be extremely slow. Artificial heat sources such as nuclear reactors or orbital mirrors to concentrate sunlight might be necessary. Next, the thin nitrogen atmosphere would need to be thickened and enriched with oxygen. Creating a breathable atmosphere requires a stable balance of gases, protective against radiation, and able to sustain liquid water on the surface. Achieving this balance on Triton would require massive engineering, perhaps releasing volatiles trapped in the ice or importing gases from elsewhere. Terraforming also means dealing with Triton's weak gravity, only about 7.5% of Earth's, which poses challenges for human health and atmospheric retention. Low gravity can affect muscle and bone density over time and might make it difficult to hold an atmosphere without constant replenishment. The Moon's retrograde orbit and potential geological instability add layers of complexity. Its slow inward spiral toward Neptune could disrupt any long-term settlement plans over millions of years. Engineers and planners would need to consider whether habitation is even feasible in the face of such celestial mechanics. Yet, despite these challenges, some visions of future space exploration and colonization include moons like Triton. Its subsurface ocean, if confirmed, could provide water and other resources. Its nitrogen-rich atmosphere, thin as it is, might serve as a starting point. And its location on the outer edge of the solar system offers unique scientific value and potential as a base for further exploration into the Kuiper belt and beyond. In this light, terraforming Triton is less about immediate practicality and more about dreaming big, about pushing the boundaries of what humanity might one day accomplish. It asks us to imagine technology so advanced it can manipulate planetary environments, energy sources powerful enough to warm frozen worlds, and a will strong enough to transform the cold silence of space into a new home. Some scientists argue that instead of attempting to terraform distant moons, we might focus on creating closed habitats, self-sustaining space stations, or underground bases that shield humans from harsh conditions without altering the environment itself. This approach could be more feasible in the near term, using local resources to support life while leaving Triton's icy landscape untouched. Terraforming Triton remains a concept caught between science fiction and distant possibility. It challenges our understanding of planetary science, technology, and what it means to live beyond Earth. Whether or not it ever happens, the very idea inspires us to look up beyond our world and consider the profound potential and fragility of life in the cosmos. Triton's frozen plains remind us of the vastness of space and the endless horizons of human imagination.
Chapter 9. The Challenge of Distance, Reaching and Living on Triton. Triton lies far from Earth, a cold sentinel orbiting the distant planet Neptune. Its remote location presents profound challenges for any future exploration or habitation. To journey there is to cross billions of kilometers of empty space through a solar system that grows darker and colder with distance. Understanding the difficulty of reaching and living on Triton is essential to grasping both its mystery and its potential. Current space missions have shown us the vastness of the task. Voyager 2's flyby in 1989 took more than a decade to arrive after launch, speeding through the outer solar system at tens of thousands of kilometers per hour. The mission lasted only a brief encounter before continuing onward into interstellar space. That short glimpse gave us invaluable data, but barely scratched the surface of what Triton truly is. Future missions face even greater challenges. A spacecraft designed to orbit or land on Triton would need to survive intense cold, low sunlight, and the long communication delays caused by distance, nearly 4 hours for signals to travel each way. Power sources must be reliable and long-lasting, likely nuclear, as solar energy is too weak to sustain operations effectively. Landing on Triton itself would be complex. Its surface is icy and rugged, shaped by geysers, faults, and ice flows. Equipment would need to withstand extreme temperatures and potential chemical hazards from nitrogen and methane ice. Exploration vehicles would have to be autonomous or remotely operated with delayed commands, requiring advanced artificial intelligence. Living on Triton presents even greater obstacles. The moon's atmosphere is thin and composed mostly of nitrogen, with trace amounts of methane and carbon monoxide, far from breathable. Pressurized habitats would be essential, designed to protect inhabitants from radiation, cold, and the low-gravity environment, which could affect human health over time. Supply chains would be long and expensive. Resupplying a Triton base from Earth would take years and vast resources. Sustainable living would require local resource utilization, extracting water from subsurface ice, recycling air and waste, and perhaps farming in controlled environments. Technological advances in closed-loop life support systems would be vital. Social and psychological factors cannot be overlooked. The isolation of living billions of kilometers from Earth, the harsh environment, and limited communication could challenge the mental well-being of any crew. Lessons learned from astronauts aboard the International Space Station and Antarctic researchers offer some insight, but Triton would be on an entirely different scale. Despite these hurdles, the scientific value of Triton is immense. Studying a captured Kuiper belt object up close could unlock secrets about the early solar system, planetary migration, and the conditions that allow life to emerge. For humanity, it represents a new frontier, a test of ingenuity, resilience, and curiosity. The challenge of distance is not just a physical barrier, but a metaphor for exploration itself. Triton reminds us how small we are in the cosmos, yet how vast our ambitions can be. To reach Triton is to push beyond familiar horizons, to step into the unknown with courage and wonder, and perhaps one day to call the moon so distant and cold, home. Chapter 10: The Search for Signs, Instruments and Missions to Come. Exploring Triton is no simple task. It is a world far away, cloaked in ice and mystery, where every clue must be gathered with care and patience. To uncover its secrets, scientists and engineers are developing new instruments and planning future missions designed to peer beneath its frozen surface and listen for the whispers of life, or the signs that life could exist. One promising proposal is NASA's Triton mission, aimed at launching a spacecraft to perform a close flyby of Triton in the 2030s. Triton's objectives include detailed mapping of Triton's surface, measuring its thin atmosphere, and searching for evidence of active geysers or plumes. By using advanced imaging and spectrometry, it hopes to reveal changes since Voyager 2's brief visit over 3 decades ago. Beyond Triton, future missions could carry radar instruments capable of penetrating the ice shell, much like the ice-penetrating radar planned for Europa Clipper. These radars can detect liquid water layers beneath kilometers of ice, helping to confirm or refute the existence of a subsurface ocean on Triton. Other instruments may focus on magnetic fields, looking for the subtle disturbances caused by salty conductive oceans beneath the crust. Measuring these fields can provide indirect but powerful evidence of liquid water, a potential habitat for life. Thermal sensors are another key tool. By mapping variations in surface temperature, they can help identify warm regions, vents, or plumes where energy escapes from below. These hotspots are especially important, as they may indicate active geology or cryovolcanism, processes that could support biological activity. Sample return missions, while more complex and distant in planning, represent the holy grail of exploration. Bringing pieces of Triton's surface back to Earth would allow scientists to analyze its composition in exquisite detail, searching for organic compounds, isotopic signatures, or even microscopic fossils. Such a mission would require breakthroughs in propulsion, autonomy, and contamination control, but the rewards could be profound. Robotic landers or even submarines designed to explore the subsurface ocean, if it exists, are dreams for the future. These explorers would venture into alien waters, shielded beneath thick ice, seeking life forms adapted to environments utterly unlike our own. It is a vision that stretches human imagination and technology to their limits. While no mission to Triton is currently funded or underway beyond concept, the moon's allure grows steadily. As discoveries of ocean worlds multiply and the quest for extraterrestrial life intensifies, Triton stands out as a unique and compelling target. Its history as a captured moon, its retrograde orbit, its active geysers, and its potential ocean combine to make Triton a world unlike any other, a distant beacon of possibility. The search for signs on Triton reminds us that exploration is never just about data. It is about hope, curiosity, and the enduring human desire to find companionship in the vast loneliness of space. Each new instrument, each new mission concept, brings us closer to answering the question that has fascinated generations. Is there life beyond Earth? Triton holds its secrets tightly for now, but with patience, perseverance, and the steady advance of technology, we may one day unlock the mysteries of this frozen moon, and perhaps, in doing so, learn more about ourselves.
Chapter 11: Triton in Culture and Imagination, From Science to Storytelling.
Triton, distant and mysterious, has not only captivated scientists, but also artists, writers, and dreamers. This moon's enigmatic nature has inspired tales that stretch beyond cold data and icy surfaces, entering the realm of imagination where science and storytelling intertwine. Since its discovery by British astronomer William Lassell in 1846, just weeks after Neptune itself was found, Triton has sparked curiosity and wonder. Its unique retrograde orbit, frozen landscapes, and potential for hidden oceans have made it a compelling symbol of the unknown, a distant world where the rules of our solar system seem to bend. Science fiction authors have long used Triton as a setting or inspiration. In the mid-20th century, as space exploration captured public imagination, Triton appeared in stories that imagined future colonies, alien life, or mysterious phenomena beneath its ice. These narratives often explore themes of isolation, discovery, and the fragile boundary between life and lifelessness in the harsh environments of space. In some stories, Triton's frozen surface hides ancient civilizations, long extinct or in deep hibernation. Others portray it as a refuge for explorers seeking to unlock cosmic secrets, a laboratory of extremes where humanity confronts its own limits. These imaginative works complement real scientific inquiry, enriching our understanding of what this distant moon could represent. Triton also holds a place in popular culture through visual arts and documentaries. Stunning images from Voyager 2's flyby and artistic renditions based on scientific data bring this icy moon to life, conveying its eerie beauty and silent majesty. These visuals invite contemplation and inspire a sense of connection across the vast gulf of space. The moon's mysterious geysers and shifting surface serve as metaphors for change and hidden depths, a reminder that beneath calm exteriors, powerful forces may be at work. This duality resonates deeply with human experience, making Triton a symbol of the unseen struggles and transformations in our own lives. Educational programs and media often highlight Triton as an example of how exploration combines observation with imagination. It encourages learners to think critically about the universe while embracing creativity and wonder. This blend of science and art reflects the broader human quest to understand our place in the cosmos. Moreover, Triton's story reminds us of the vastness and diversity of the solar system, challenging assumptions about habitability and life. It urges us to look beyond Earth-centric perspectives and appreciate the myriad environments where life might exist or begin. In this way, Triton acts as a bridge between the known and the unknown, the factual and the fictional, the scientific and the poetic. Its silent orbit around Neptune echoes through culture as a beacon of curiosity, inviting each of us to imagine worlds beyond our own and to ponder the mysteries that await discovery.
Chapter 12, Reflections and the Future, What Triton Teaches Us. As we draw near to the end of our journey through the mysteries of Triton, Neptune's distant moon, it is fitting to pause and reflect on what this frozen world teaches us, not only about the cosmos, but about ourselves. Triton is a place of contradictions. It is both ancient and active, silent yet restless. Its surface is a shimmering expanse of ice, yet beneath lies the possibility of hidden oceans, geological energy, and chemical complexity. This duality reminds us that appearances can be deceiving, and that beneath quiet exteriors, profound activity may pulse. The story of Triton challenges our understanding of habitability. It expands the boundaries of where life might exist beyond the familiar warmth of Earth-like planets to the cold, dark corners of the solar system. It invites us to consider that life is resilient, adaptable, and perhaps far more common than we once believed. Our knowledge of Triton remains limited, a testament to both the vastness of space and the infancy of our exploration. Yet even from afar, Triton inspires awe, a beacon beckoning us to continue searching, learning, and imagining. Looking forward, the future of Triton exploration is bright with potential. Upcoming missions like Triton could unveil new details, while advances in technology may one day allow us to penetrate its icy shell, sample its plumes, and search for signs of life firsthand. But Triton's lessons reach beyond scientific inquiry. They remind us of the value of curiosity, perseverance, and wonder. In a universe so vast and varied, every world, even one as remote and cold as Triton, holds stories waiting to be told. As we close this chapter, let us carry with us the spirit of exploration embodied by Triton, a spirit that looks beyond horizons, that embraces mystery, and that honors the delicate balance of life and environment. Whether or not we ever find life beneath its ice, Triton's existence challenges us to keep dreaming, keep seeking, and keep listening to the silent music of the cosmos. In the end, Triton teaches us that the universe is not just a collection of stars and planets. It is a vast canvas of possibility, inviting us to wonder what lies beneath the surface and to imagine what might be.
Conclusion: embracing the mystery of Triton. As we come to the close of our exploration of Triton, we find ourselves standing on the edge of knowledge and imagination. This distant moon, circling Neptune in the cold depths of the solar system, remains a world of mystery, a frozen orb whose secrets have only just begun to unfold. Throughout our journey, we have glimpsed the remarkable features that make Triton so compelling. Its active geysers breathing nitrogen into a thin atmosphere, its smooth, icy plains shaped by forces unseen, and the tantalizing possibility of a hidden ocean beneath its frozen shell. These clues suggest a world that is alive in its own way, not with the green forests or warm seas we know on Earth, but with quiet geological energy and the slow, subtle chemistry that might, just might, support life. Triton challenges us to expand our definition of what it means to be habitable. It teaches us that life might endure in places beyond our familiar experience, in darkness, under crushing ice, and far from the nurturing warmth of the sun. Our knowledge of Triton remains incomplete, a mosaic of data points gathered by brief spacecraft encounters and careful telescopic observations. Yet even in this limited light, the moon calls to us, inviting us to learn more, to imagine possibilities, and to continue the search for life beyond Earth. The future holds promise. New missions may one day return to Triton, equipped with the technology to peel back its icy veil and explore its depths. Until then, we listen and watch, our curiosity undiminished. In the silence of space, Triton spins, a solitary world, a cosmic enigma, and a symbol of our enduring quest to understand the universe and our place within it. As we embrace the mystery of Triton, we also embrace the wonder of exploration itself, the journey toward knowledge, the thrill of discovery, and the hope that somewhere out there, in the cold and quiet, life finds a way.